Welcome to AI Paper Slop, the YouTube series for AI researchers, ML engineers, and, anyone building in the trenches. Our goal here is to give you the absolute most crucial technical updates without the fluff. So today we are tearing into a paper called Latent Reasoning with Normalizing Flows, or NF-CoT. This is by researchers at UPenn, UC San Diego, and Meta.
Right, and it is a massive architectural shift.
It really is. So let's get straight to the core insight right out of the gate. We all know explicit text-based chain of thought is incredibly effective. I mean, it's basically the backbone of modern reasoning models, but it is also horribly inefficient because it forces an LLM to think using a discrete, serial, low-bandwidth token stream.
Exactly.
NF-CoT fixes this bottleneck. It pushes the reasoning entirely into a continuous latent space using normalizing flows. And the numbers on this are just insane.
Yeah, the performance metrics are, frankly, exactly what you want to see if you're actively deploying these models and wrestling with, well, massive inference costs. They managed to compress 385 text tokens of explicit reasoning into just 64 continuous latent tokens.
64.
Right, which is a 6.0x compression rate. And it runs 2.7x faster than prior diffusion-based latent models like Ladeer.
That's a huge jump in speed.
It is. Plus, it preserves exact autoregressive likelihoods for left-to-right decoding, natively supports your standard KV cache, and get this, when they applied it to a Qwen 3.8b base model, it boosted the code generation pass rate by 13% across 5 major benchmarks.
Okay, let's unpack the mechanics of this, because to really understand why NF-CoT is such a massive leap, we need to talk about why standard chain of thought is fundamentally a bottleneck for our infrastructure.
A huge bottleneck.
Right. So imagine forcing a brilliant mathematician to solve a really complex topology problem, but legally requiring them to speak every single arithmetic step out loud in English before they're allowed to write down the final answer.
That sounds agonizing.
It is, but that is exactly what we are doing to LLMs. When a model outputs text tokens to reason, it's forced to use human language. And language is a communication-oriented medium. It's highly verbose and incredibly low bandwidth for a machine.
Right, and you're forcing the neural network to articulate semantic, partially formed mathematical updates into discrete English vocabulary at every single step. It's just a low information density medium for internal thought.
Exactly. Forcing a model to verbalize every intermediate computational step just wastes massive amounts of compute, and it ties the reasoning tightly to surface forms.
Which means the model gets bogged down in syntax and vocabulary rather than, just doing pure logic.
Yeah, and this inefficiency is exactly why the field has been trying to build latent CoCo methods for a while now. We want to let the model do the math silently in its head. But previous attempts fell into what we can categorize as the latent trap.
The latent trap, yes. They tried to create a silent thought space, but in doing so, they basically broke the fundamental mechanics of how LLMs operate.
I want to dig into those previous attempts for our listeners just to highlight the specific problem this paper solves. So let's look at an approach like Coconut. From what I understand, Coconut uses deterministic hidden states for its latent reasoning.
Right, it does.
So it's fast, but it seems like it completely sacrifices the ability to explore multiple solutions.
That's the core issue with deterministic states right there. Coconut is very computationally efficient, but because the continuous state is entirely deterministic, it lacks probabilistic sampling.
So it just goes down the exact same track every time.
Exactly. If you prompt the model to solve a complex coding challenge, you can't sample diverse reasoning paths. It essentially walks that exact same rigid path every single time.
Which is not what you want for complex reasoning.
No, not at all. So to counter that, you have approaches on the other end of the spectrum, like Ladeer. Now, Ladeer uses diffusion models to handle stochastic continuous latents, which does give you that necessary diversity.
But diffusion introduces a massive latency penalty. Right?
Oh, absolutely. Yeah. It requires iterative denoising. And Ladeer's specific implementation, that means 30 slow, sequential denoising steps just to generate the continuous thought.
30 steps per thought. That's brutal.
That's very slow. But more critically, diffusion models lack native left-to-right likelihood modeling.
Which seems like a total deal breaker if you're working with an autoregressive LLM. I mean, the entire transformer architecture we rely on is built around predicting the next token based on the likelihood of the previous sequence.
Exactly.
If you use diffusion for the thinking phase, you're effectively stripping away the native sampling, the scoring, and the decoding interface that these models are built around. It feels like, I don't know, trying to run a combustion engine underwater.
That's a good way to put it. The fundamental engineering challenge the researchers faced was how to achieve continuous high-bandwidth reasoning without giving up those exact autoregressive likelihoods that make modern LLMs so scalable.
You need a continuous space that acts mathematically identical to a discrete token space.
Right. You need a mechanism that allows the model to compute probabilities, sample left to right, and maintain that linear flow. And the mechanism they use to achieve this is normalizing flows.
Normalizing flows. I think for a lot of engineers listening, this might be a concept they haven't implemented from scratch recently.
Yeah, it's not as common as standard transformers these days.
Right. So because diffusion is too slow and deterministic states don't let you sample diverse thoughts, NF-CoT uses a scalable normalizing flow to build an LLM-facing continuous thought space.
Specifically, they base this on StarFlow and TARFlow architectures, utilizing a causal Gaussian density.
Okay, can we break down the actual training pipeline here? Because they use a two-part process involving a pre-trained text VAE-SO, a variational autoencoder.
Yeah, the pipeline is quite elegant. Let's start with the VAE. The VAE's job is translation. They take explicit chain of thought text like the actual human-readable logic, the verbose step-by-step reasoning, and they feed it into the frozen VAE encoder.
Okay, so feeding standard text into the VAE.
Right, and the encoder maps that verbose text into a dense, continuous latent space, which they denote in the paper as the variable E.
Got it.
The problem is that this raw latent space E is not formatted in a way that an autoregressive LLM can naturally read or write token by token.
Okay, and this is where I'm trying to wrap my head around the compression aspect. If we are taking 385 highly specific text tokens, we're talking variables, syntax, logic gates, and squeezing them into just 64 continuous slots using a VAE, aren't we inherently losing vital information?
That sounds like you would, right?
Yeah. Compression usually implies loss, and in complex code generation, dropping a single variable reference breaks the entire program.
That intuitive concern is absolutely valid, and it's precisely why the normalizing flow is the critical bridge in this architecture. To fix this, they introduce what are called shallow flow blocks.
Shallow flow blocks.
Yes. Specifically, they use 5 autoregressive flow blocks, which they call metablocks, with alternating permutations. The whole purpose of these blocks is to take those raw VAE latents, E, and reparameterize them into a new sequence, denoted as up.
Okay, so mapping E to U.
Exactly. This new sequence is shaped so that the LLM can easily sample and score it. And here's the magic of a normalizing flow. These shallow flow blocks are mathematically invertible.
Oh, wait. So because the transformation is invertible, the map space is strictly information equivalent to the VAE latency?
That's exactly it.
So by definition of the math, there is zero loss of information during that reparameterization step. The data isn't being compressed further or degraded, it's just being reshaped.
Yes, you are basically warping the continuous geometry so that the LLM can read and generate it autoregressively, moving from left to right using the exact same mechanisms it would use for standard discrete tokens.
That is so clever. You're building a mathematical bridge between the dense, complex representation of the VAE and the sequential step-by-step interface of the LLM.
Exactly. The flow blocks ensure the LLM can navigate that dense space without losing the semantic meaning of the reasoning.
Here's where it gets really interesting for anyone managing inference infrastructure and, trying to optimize latency.
Yeah.
Now that we have this invertible mathematical mechanism for latent thoughts, we need to know how it actually plugs into the physical architecture of the LLM.
Right, the actual deployment side.
Because the researchers tested this on a shared LLM backbone, specifically QEM3 8B base, using a dual head setup. And they tested 2 different inference paths, a dual path variant and a unified path variant.
Yeah, so the dual path variant was their baseline approach. In that setup, the model processes the flow density, which is the continuous reasoning, and the standard cross-entropy path for text generation completely separately.
So 2 disjointed tracks.
Right. It functions, sure, but it requires disjointed processing. The real breakthrough in efficiency comes from the unified path variant, which interleaves the processes.
The unified path essentially puts everything onto one single causal stream. You have the NF head, which outputs the continuous thought positions, specifically the Gaussian parameters, mu and sigma.
Yes.
And sitting directly alongside it on that exact same QEM3 backbone, you have the standard LM head, which outputs your traditional discrete text answer positions.
And if we look at the mechanics of the KV cache, the unified path is a dream for memory optimization.
Yeah, let's talk about the KV cache, because that's where the magic happens.
Exactly. So the KV cache, or the key value cache, is basically the memory bank an LLM uses to store the context of previous tokens. That way, it doesn't have to recompute the entire sequence at every single step.
Which would be impossibly slow.
Right. So in the unified path, during inference, the LLM begins by sampling those continuous thoughts left to right using the NF-head. As it does this, it is building up a standard KV cache, just like it normally would for text.
Okay, so it's populating the cache with latent thoughts.
Exactly. And when the model determines it has finished thinking and it's time to generate the actual human-readable text answer, it simply switches over to the LM head.
And because it's on the same causal stream, it continues decoding using that exact same KV cache. It doesn't have to flush the memory or recompute the context.
Not at all.
I'm picturing this like a continuous assembly line in a factory. The first half of the belt is highly specialized. It builds the complex internal engine, which represents the latent thoughts.
I like that analogy.
Thanks. Then, without ever stopping the build or taking the car off the line, it reaches the second half where the robotic arms smoothly drop the chassis, the discrete text answer, right on top of the engine.
That's a perfect way to visualize it. And the efficiency gains over a diffusion-based model like Ladeer are driven entirely by this seamless transition and the fact you avoid iterative denoising completely.
And the benchmarks show that, right?
Oh, absolutely. We're looking at 2.7x faster latent generation, dropping from 468.2 seconds down to 173.5 seconds for a batch of candidates.
Wow.
And the total runtime is 1.9x faster. But critically, for the bottom line of compute cost, is 2.48x cheaper in per sample compute. The requirement drops from 49.3 teraflops per sample down to just 19.9 teraflops.
Those numbers are massive for deployment. I mean, having your FLPs is incredible, but from a training perspective, slapping a radically different mathematical head, this normalizing flow head onto a highly optimized pre-trained LLM like Qwen3 sounds incredibly unstable.
It is extremely risky.
Right. If you just unleash raw gradients from a randomly initialized flow branch onto an 8 billion parameter model, wouldn't it cause catastrophic forgetting? Wouldn't it completely scramble the model's existing coding, syntax, and reasoning abilities?
The risk of catastrophic forgetting is severe in this context, and that is exactly why the researchers designed a highly controlled two-stage training curriculum. You simply cannot joint train everything from scratch and expect the pre-trained weights to survive the shock.
So what's the first stage?
Stage 1 is entirely about calibration. They freeze the LLM backbone completely. The only parameters that receive updates are the shallow flow blocks and the continuous thought projection layers.
So the warm-up stage acts as a protective buffer. You are essentially calibrating the interface.
Yes.
It's like installing a highly advanced aftermarket steering column into a sports car. You don't just jam it in while the engine is running and hit the gas.
That would be a disaster.
Right. You lock the wheels, wire the sensors, and make sure the translation between the wheel and the tires is perfectly synced before you actually drive. It ensures the model has a stable, mathematically sound interface before it tries to learn this totally new way of processing information.
That's exactly what's happening. And the ablation study provided in the paper really highlights the exact cost of skipping that calibration.
Oh, they tested skipping it.
They did. They ran a separate test where they bypassed stage 1 entirely and went straight to full joint fine-tuning, unfreezing all parameters immediately. The result was severe backbone drift.
How bad was the drift?
Well, by skipping the warm-up, the relative L2 distance drift in the final transformer layer increased by 18%.
Wait, 18%? That is a staggering amount of drift for the final layer of a pre-trained model. I mean, that layer is responsible for the final feature representations before the model commits to a token.
Exactly. That final layer is the shared representation bottleneck that feeds both the LM head and the new NF head. When it gets hit with early, uncalibrated, chaotic gradients from the flow branch, it fundamentally disrupts the core representations the model relies on for basic Python syntax and logic.
And I imagine that trashes the benchmarks.
You see the damage immediately in the downstream metrics. The human evil coding score dropped from 84.4 down to 81.5 solely because they skipped that stage 1 warm-up.
Okay, so through this curriculum, we have established that NF-TT is stable. It is an incredibly efficient, continuous reasoning model that actually retains its ability to write clean code.
Yes, it works beautifully.
But if we pivot to the current state of the art for reasoning models, looking at the landscape shaped by models like DeepSeek R1, the gold standard right now is reinforcement learning. Supervised fine-tuning only gets you so far.
That's very true.
So the lingering question for me is, can we actually optimize these silent, continuous thoughts using RL, considering we don't have discrete tokens to score?
This is arguably the most powerful technical advantage of the NF-CoT architecture. Because the normalizing flows provide exact tractable likelihoods, which, again, diffusion models cannot easily provide without heavy approximations, you can apply reinforcement learning directly into the continuous reasoning space.
Direct RL on the latents.
Exactly. The researchers implemented GRPO, Group Relative Policy Optimization, directly on the latents.
And for our listeners, GRPO is highly popular right now because it doesn't require a separate, massive critic model. You generate a group of answers, score them based on a reward like whether the code actually executes and passes the test, and then update the policy to favor the steps that led to the correct outcome.
Right, it's very efficient.
But normally you absolutely need discrete text tokens because you have to calculate the exact probability of that specific sequence to update the policy.
Right, and because the flow is invertible and gives you those exact probabilities, the math translates perfectly to the continuous space. They ran an execution-guided RL experiment using a mixture of 20,000 Python problems.
And what were the results?
The RL stage pushed the overall benchmark average from 68.8 to 70.1. Now, while a 1.3-point bump might sound modest on the surface, the underlying sampling dynamics reveal a much deeper architectural victory.
Let's talk about those dynamics, specifically the pass at k-scaling. Because any engineer who has run standard token space RL knows you inevitably hit a wall, right? The dreaded mode collapse.
Mode collapse is the absolute bane of token space RL. Standard token space GRPO is highly effective at improving pass at 1, meaning the model's likelihood of getting the right answer on its very first attempt goes up.
Which is great.
It is great. However, the RL algorithm tends to find one successful linguistic or algorithmic path and just concentrates all its probability mass on that single mode.
Right.
So when you increase your sampling budget, say, generating 128 different answers to find the best one, which is your pass at 128, the performance flatlines, the model just spits out 128 minor syntactic variations of the exact same algorithm. It stops exploring new, diverse solutions.
It stops innovating. It just keeps repeating the same slightly tweaked idea over and over. But the data shows that NF-CoT with RL maintains high diversity, doesn't it?
It does. It preserves that upward pass at k-scaling trend at budgets, all the way up to 128 samples. The continuous space doesn't collapse into a single point.
So if the pass at k-scaling remains intact, does that suggest the model is actually exploring fundamentally different algorithmic solutions in its head, rather than just slightly tweaking variable names in one single idea?
The researchers wanted to verify that exact hypothesis. They didn't just look at the raw pass rate. They actually probed the latent space to prove that genuine algorithmic exploration was happening.
Okay.
And this brings us to their qualitative analysis, which is essentially decoding the shape of the thought process.
It's basically mind-reading the model, trying to translate a multidimensional continuous vector back into something an engineer can actually debug.
Exactly. The challenge, of course, is that continuous latents are inherently alien to human readers. You can't just read the matrix. So to interpret them, the researchers utilized the frozen VAE decoder from their training pipeline.
Ah, running it in reverse.
Right. They took the continuous latents generated during inference and ran them backwards through the decoder to translate them back into English text. But they include a massive caveat that this isn't a flawless one-to-one faithful English explanation of the model's internal matrix operations.
Right, it's a qualitative probe. It is a way to get the gist of the mathematical shape of the thought, to see what kind of logical structure the model was leaning toward before it output the final code.
The qualitative results are stunning, though. They analyzed a specific coding problem called fib-fib.
Fib-fib.
Yeah, it's a complex variation of the Fibonacci sequence that requires tracking multiple previous states. When they sampled multiple continuous thoughts for the exact same prompt, the latents reliably translated into entirely different, fundamentally correct algorithmic strategies.
Wow. So when they decoded one latent sample, it showed the model guiding itself toward a rolling state dynamic programming solution.
Yes.
And then they decoded a different latent sample for the same prompt, and it showed the model internally planning an explicit tabulation approach using arrays.
Exactly. And a third sample revealed a plan for recursive memoization.
That is wild. So the latent space isn't just capturing surface-level textual variation or swapping variable names. It is capturing genuine algorithmic diversity.
It is selecting fundamentally different time and space complexity approaches. And to further prove how robust and well-structured this continuous space is, they ran a latent perturbation robustness test.
I was reading that part and thinking, this is so clever. What did they do?
They actively injected Gaussian noise directly into the continuous latent trajectory during inference.
So what does this all mean? They deliberately corrupted the thought process to see if the logic would break. I really want to highlight the numbers on this because they are wild. When they injected that Gaussian noise, the exact text match of the generated code plummeted. It dropped from 0.973 all the way down to 0.278. The output code looked completely different on the surface.
Right, but look at the correctness.
Yeah. The functional correctness, the pass at one execution metric, remained almost entirely stable, dropping insignificantly from 86.0 to 83.6.
It barely moved.
It's incredible. I picture this like turning the steering wheel on an incredibly wide multi-lane highway. You are injecting variance into the steering. You aren't crashing the car into the barrier, and you aren't breaking the code's structural correctness. You are just smoothly shifting the model into a completely different lane to arrive at the exact same correct destination.
That robustness proves that the NF-CoT latent variables act as distributed control variables over the solution trajectories. The noise doesn't shatter the logical structure because the continuous space is semantically smooth. It just smoothly shifts the model into a different valid implementation style. It is a level of flexibility, efficiency, and resilience that explicit discrete text tokens simply cannot match. I mean, changing a single discrete token often breaks the compilation entirely.
Oh, easily. One wrong bracket and you're done. Well, that wraps up our analysis of the source material for today on AI paper slop. Thank you for joining us for this breakdown.
Always a pleasure.
But before you get back to your own deployments, I want to leave you with a final thought to chew on regarding where this technology is heading. If NF-QE can successfully compress 385 tokens of human-readable logic into 64 continuous slots, and we have proven we can apply reinforcement learning directly to this latent space based purely on execution rewards.
The execution rewards are key.
Right. So what happens when we stop bootstrapping these models with human text altogether? The VAE in this paper was trained on human chain of thought. But what happens when the RL process runs for millions of iterations without a human text anchor?
That's the real question.
Could future LLMs invent their own entirely alien, highly optimized, multidimensional reasoning language? A language that we literally cannot read or decode, but that solves complex coding and math problems exponentially faster than human logic ever could. It's something to think about. Check out the paper, Latent Reasoning with Normalizing Flows, to see the exact architectures and math for yourself, and we will catch you in the next breakdown.